Okay, now you should be able to hear. Okay. Let's start with. So we formulated Newton's laws of motion. We wrote down Newton's law of gravity. We talked about apparent weight. We talked about normal force or reaction force. So now I just have to say a few words about friction and, well, tension forces are simple in a sense that it is easiest to introduce them just by solving a problem in which we have some string and, or a cable. So let's friction forces. That's it. So, okay. So let's start. So you have two objects in contact, like this remote control on top of the table here. So you have, due to this contact, there is a normal force perpendicular to the surface of the contact. However, in addition to that normal force, there is a friction force. So if I push a little bit this remote control, it doesn't move, especially if it is something heavier like this laptop. If I push it, I apply force, and there is no acceleration. So what is going on? What's going on is that there is a friction force between the laptop and the table, and that friction force cancels out the force that I'm applying. So that friction force is called static friction force if the object is not in motion. And you can experimentally verify that the static friction force, let's use a different notation, maybe lowercase f for static friction force, and I'm going to put a superscript max. It can be demonstrated experimentally that the maximum value that the static friction force can achieve is proportional to the normal force. And there is a coefficient of proportionality mu s, which is called coefficient of static friction. And the coefficient of static friction depends upon the nature of the materials in contact. So it is some dimensionless number. Now, notice the subscript max for the static friction force. It tells you that, in a sense, static friction force is a smart force. So it registers how much force I am applying, and it cancels it out. It generates a static friction force in opposite direction with the same magnitude up until some point. If I apply a force that is too large, I'm going to exceed that maximum value, and in that case, there is no static friction anymore because the object is in motion with respect to the table. So the smartness of the friction forces is in the fact that they feel the direction of the external forces and their magnitude and match them if they can, especially the static friction force. If it can match the external force, it does. And the maximum value that it can match is this one. Now, once the object starts moving, there is still friction. However, this friction is called kinetic friction, not static friction. In general, it is smaller friction force than the maximum value of the static friction force. So this is why when you get something moving, it is easier to keep it moving just because the kinetic friction force is smaller. Again, experimentally, you can verify that the kinetic friction force is equal to the coefficient of kinetic friction, again, depending upon what is the nature of the materials in contact, that coefficient has different values, multiplied again by the normal force. So the kinetic friction doesn't have a maximum value. It has only one value given with this expression. Now, something that is surprising but correct. Okay, I'm going to use this. Both the static and the kinetic friction forces are the same for this object, no matter if this object is this way, or this way, or this way. In other words, what is the area of contact between the surfaces doesn't matter. It doesn't enter the equations. Now, it's surprising, but we're talking about ideal case in a sense that there are no, the two surfaces in contact are smooth. There are no things that can catch, and in that case, of course, yes.
How would that relate to a water tension? Because I know if you have something that's a wider base for water tension, kind of.
So water tension is not quite, it is not quite friction force. So friction forces, just like the normal force, friction forces are due to electromagnetic interaction between the molecules of the two objects. So the tension force is due to the interaction between the molecules of water. That's it. So basically, surface tension is, well, this is one of the forces that we're not going to study, but it is interesting because, well, you're asked to wash your hands with soap. And what the soap does is it reduces the surface tension of water and, in a sense, makes the water enter places where otherwise it wouldn't.
It's also both hydrophobic and hydrophilic,
yes.
So it dissolves fat and non-fat.
Yes. So again, those are interesting things. But well, we have so far gravitational force, normal force, two friction forces, and we're going to encounter questions related with tension of cables and things. So that's going to be pretty much enough for the forces that we study are going to be enough to well, to solve a wide range of problems. So on all of this, let's see some practical application about friction forces and similar expressions. So let me. So you are asking. Yeah, let me just first see if I have profile here. So people on Zoom, hopefully everybody is working well and hard on the midterm test. If you have questions, you can talk with the tutor or you can talk with me. But well, today is Thursday. The test is due tomorrow at midnight. So don't leave it for the last minute. So let's see problem number. Let me look at the problems so that start with some problem that is useful. So people on Zoom actually have the homework assignment on their computers so they can look at the homework assignment and also the solution on the board. So this probably is the longest homework assignment for the semester. You're not going to have homework assignments that are that long anymore.
The Zoom feed is up there. Is that what you intended, or?
Oh, is this, oh,
Yeah, it's the Zoom feed off this computer.
yeah. Let's look at the computer. Okay. So let's start with problem number 20 from homework 4. So the problem is about Mercedes 300 SL with given mass parked on a road that is inclined to 20 degrees above the horizontal. Find the magnitude of the normal force, find the static friction force. So this is very standard and very key problem, because very often we're going to solve problems about objects that are on inclines. So let's start maybe with the diagram first, maybe. Here is the road. This is the horizontal. And here you have your 20 degree, or let's make it angle theta. Theta equals to 20 degrees with respect to the horizontal. And here is the vehicle. The car is right here. But the first question, so they give you the mass of the car, and they give you the angle of the incline. The first question is to find the magnitude of the normal force. Normal force is what? Well, of course, a diagram, and use the fact that the object is at rest. So the object is at rest. This means that all forces acting on this object cancel out. So let's see what are the forces present. So you have the weight, gravitational force, mg, in this direction, downward, vertically downward. The normal force is perpendicular to the surface of contact. So it is this way. Now, they're asking about friction forces. So friction forces are smart forces. What is the direction of the friction force? It is parallel to the surface. But is it down or up? Well, if there were no friction, this object would slide this way. Therefore, the friction is in opposite direction. So static friction this way. This is the free body diagram. This type of diagram you need for every problem related to which forces, accelerations, and so on. Now, look, we need a coordinate system. And probably a convenient choice for a coordinate system would be x-axis parallel to the surface and y-axis perpendicular to the surface upward, let's say. Well, it doesn't matter which way. Upward is the origin of the coordinate system at the center of mass of the object. Well, in this coordinate system, why this coordinate system is more convenient? Because in this coordinate system, the normal force is along y-axis. It doesn't have x component. This simplifies things. And the friction force is along the x-axis. Therefore, the friction force doesn't have y component. This makes this coordinate system convenient. It is convenient, but not perfect. The gravity force, the weight, has x and y components. And it is good if we realize that, and we have to decompose in order to cancel out all the forces. We have to decompose the gravity force into x and y components. So here is the y component of the gravity force. Here is the x component of the gravity force. And the gravity force itself, of course, is the hypotenuse of the right triangle that is formed. Now, we know the hypotenuse of the right triangle that is formed by the components of the gravity force. We know that the components are perpendicular to each other. So we have two numbers for this triangle. We need one more number in order to figure out the magnitudes of the x and y components of the gravity force. And that additional number comes from geometry. This angle of the right triangle has to be exactly equal to the angle theta, in my case 20 degrees. Why? Because in geometry you have a theorem which says that if you have two angles with mutually perpendicular arms, those two angles must be equal. And you see that this arm of the small triangle is perpendicular to the dashed line, and this arm is perpendicular to the surface. Therefore, you have two equal angles, therefore this angle is 20 degrees. And now I can write the magnitudes of the components of the gravity force. So this component is it is adjacent to the angle theta side, so it is mg cosine of the angle theta. Notice that that component is in negative y direction. So strictly speaking, it is with negative algebraic sign. I just will write its magnitude for the moment. And the other component, the x component, is mg sine of the angle theta. Now, once we have those forces, it is easy to answer their question. So, in order an object to be at rest, not to accelerate in any direction, you need all forces to cancel out. Well, this means all forces in x direction to cancel, and all forces in y direction to cancel. Well, in y direction, we have only normal force and this component of the gravitational force, of the weight. So they have to cancel. There is no other way. If they were not equal in magnitude, this car either would fly above the pavement or sink below the pavement, which doesn't happen. So the normal force must be equal in magnitude to the y component of the weight. And this should be the answer. So the mass of the car is given, the angle is given, you just multiply those numbers. So normal force, okay, I'll write it right here. F normal is mg cosine of theta, and I know that because otherwise F normal and the y component of the weight wouldn't cancel, and they do cancel. So this answers their first question. So this is the answer to part A. Part B, what is the static friction force exerted on this car? What is the static friction force? Well, again, the x components, the forces in x direction also have to cancel out. Otherwise, the car is either going to slide down or it's going to go upwards, which is not what the problem says. Therefore, you have the static friction force should be equal to the only other force in x direction. This is the x component of the weight. Should be equal to mg sine of the angle theta. Okay. Let's see questions about this problem.
So are M and G really negative? And then since you multiply to negative.
No, I just wrote their magnitudes, and I'm only working with magnitudes.
Okay.
So only with absolute values. So I see from the diagram that mg cosine, this component of the gravity, is in negative y direction. And I see again that the normal force is in positive y direction. In order they to cancel out, only their magnitudes have to be equal. Their directions are already opposite.
And G for that equation is 9.8.
G is 9.8. So in this problem, they could have asked something in addition to what they are asking. But let's leave that for a different problem. Let's go to any questions from Zoom? Any questions from people online? Okay, if no questions, let's go to problem number. Okay, let's go to problem number 21. Problem number 21. Important problem for anybody that wants to go to dental school, and also anybody that has to. So you have a drawing, and so you have some wire brace, and the tension in this wire brace is certain tension, and they show two tension forces. The forces have the same magnitude of 15 newtons. What is the magnitude of the net force exerted on the tooth by those braces? Okay, so I guess I'm not going to try to redraw the diagram that you see on the screen, but basically they're saying that this wire right here is under tension. On this side T, on this side T prime, and both T and T prime have magnitude of whatever number of newtons, 15 newtons in this case. And they're asking about what is the net force that those two tension forces generate. So notice that those two tension forces, well, they are not exactly in opposite direction, but they have components that are in opposite directions, and those components are going to cancel out. So let's see how this works. Okay, so here is probably So here is the first force, T prime, the second force, the same in magnitude, but different direction. Here you have some horizontal line, and they give this angle between the horizontal line and each of the forces, and that angle is the same. It is 16 degrees. Well, I just will call it angle theta. So it is the same angle on both sides. So you have two forces. What is the magnitude of the net force? This is practically what the problem says. And look, use some coordinate system, maybe a coordinate system with x-axis horizontal, y-axis in downward direction. Y in downward, just work with positive numbers. So in this coordinate system, you can decompose the tension forces into components. So here is Ty, and this is the component Tx. Similarly, T prime y and T prime x. Now, the triangles formed by those two forces and their components, the two triangles are equal triangles. They have the same angle, the same size. They should be equal triangles. Right? They're also right triangles, of course. Here's the right angle. Well, what can you say about the x components of the force Tx and T prime x? Those components right here, this and this component. Well, they're in opposite directions and they have the same magnitude, therefore they cancel out. While the y components are in the same direction. So they add up they add up like numbers because they're in the same direction. So the net force is equal to, well, the force Ty, but twice, because Ty prime is the same. In other words, looking at the triangle, it is 2 times the value of the force T that they give you, multiplied by sine of the angle of 16 degrees. And that should be the answer. This is the magnitude of the net force.
Can
Yes.
I make recommendations?
Yeah.
Where you're at, that's actually really good.
Okay.
Keep it straight in there.
Also, it is up to here, up to here.
Yeah. We had a request.
Great, thank you. Okay, so let's see questions and remarks. Okay, let's go to so this problem 22. Let's do problem number 22. So this one is probably a little bit. Okay. So this problem seems quite challenging. Let's see how it's going to go. Problem 22 from the homework. So this is the end of it. So a person in the drawing is standing in crutches. The force exerted on each crutch by the ground is directed along the crutch as the force vectors in the diagram indicate. If the coefficient of static friction between a crutch and the ground is given, determine the largest angle that the crutch can have just before it begins slipping. Okay, so a single crutch, we're looking for the maximum angle taken here. it is related with static friction. So let's figure out, let's draw the diagram. So here is the crutch, and here is the vertical line, and the angle theta between the vertical and the crutch is here. And the force that the ground applies to the crutch is this way, F, force F. So the only number that they give you is the coefficient of static friction. Some number. Well, look. First, is the force with which the ground acts on the crutch, what kind of force is that? We have only two forces that appear in the case of a contact between two objects. We have normal force and we have friction. Normal force perpendicular to the surface, friction parallel to the surface. Static or kinetic still parallel to the surface. So the force that they show here is neither perpendicular to the surface, nor it is parallel to the surface. So doesn't seem to be anything familiar. In reality, you have to interpret that force as normal force plus static friction. So when you add one force that is perpendicular to the surface, normal force, and one force that is parallel to the surface, friction force, you get a force that is under certain angle. That's it. So this force F is the net force. And for that force, if you use a coordinate system that is natural coordinate system, x, y axis like this, here is the force. So you have the parallel component must be the static friction. And of course, the perpendicular component must be the normal force. But let's say that the diagram that we have now, the angle theta is the maximum angle. The angle that we're looking for. So look what happens in that case. If theta is already the maximum angle, we have a relation between the friction and the normal force. It says that friction static max is equal to coefficient of static friction times normal. Well, once we have that relation, look at the diagram. Look at the diagram, and let's say express tangent of the angle theta. The tangent of the angle theta is going to be the friction force, static friction, divided by normal. But the friction force is coefficient of friction times normal. In denominator, you have normal. Normal force cancels out. And you get a simple trigonometric equation. Tangent of the angle that you're looking for is exactly equal to the only number that they give you, the coefficient of static friction. In other words, the angle itself is equal to inverse tangent of coefficient of static friction, and this should be the answer. So what solved this problem was the realization that the horizontal component of this net force F must be friction, while the vertical component must be normal. Because there are no other contact forces between both. Only friction and normal force. Questions?
I think it was just one set. Did anyone having a problem figuring out the angle on the last problem?
Problem 11 from where? Problem 11 from homework assignment, which homework assignment, or from practice test? Okay, they have to answer. Homework 3. So homework 3 was due a little bit earlier. So we have to talk in private for this problem, problem 11. I solved it in class probably at least twice. In their YouTube videos that you can review, but it is also, the other option is we to meet and solve this problem together with explanation and diagrams and everything. And I'm going to change the deadline for you so you to be able to enter the solution. But we have to talk. There is no way to communicate arithmetic, algebraic solutions with diagrams just by Zoom, just by talking. So probably good time would be tomorrow between 12 and 1 o'clock. Just find me in the office and we can solve this problem and any other problem that that you want to see. Okay. Let's now go to problem number 23. Okay, so this problem has strings and therefore tension forces are going to be used. And usually with problems that include strings and tension forces, therefore, you usually have to apply the action-reaction law. So the action generates a reaction. So let's see how this problem works. Problem 23 from the homework. So you have a drawing and the two blocks. What they give you is not the mass, but they give you the weight of those blocks. So we have to be careful not to mess up those things. They say that there is no friction, and first you have to find the acceleration. Okay. Now look. Let's draw the diagram. So here is the first block. And the surface. And after that, you have some pulley and string. And here is the second block hanging like this. And this is kind of. So they don't give the masses, they give the weights. But you can figure out the mass of each block, and it is going to be needed. But before we continue, let's select a coordinate system here. So let's use a coordinate system that has positive axis this way, and positive y-axis this way. And you need a coordinate system actually, if you have chosen the y-axis to be up, you have to be a little bit more careful. The reason is this: you want, when one of the blocks is moving in positive direction, the other one also to be moving in positive directions. Otherwise, you have to use two different coordinate systems, and you have to be careful with the algebraic signs. It is easier just to start with a single coordinate system that has this orientation of the axis. Well, let's say that the mass of this block is m1. So the forces that act on this block are gravitational force m1g. And what other force? They say no friction. Therefore, the only other force is normal force F normal 1. Oh, there is a string attached, and that string is going to pull the block with tension force T1. So those are the forces. And actually, I'll put this tension force here. So all the forces to act at the center of mass of the block. Do we know the value of, well, they tell us that the weight of the first block is certain number, and this is exactly the number that we need, right? So this is, call this, let's say, I'll call this, call it weight W1. And W1 is given. So this is the free body diagram for the first block. Now we have to draw a free body diagram also for the second block. So for the second block, you have the weight is M2G, and it is given, it is W2. And the only other force that acts on the second block is a tension T2. Now, here comes the action-reaction situation. Newton's third law. Newton's third law requires the action and the reaction to be equal to each other. In other words, the force T2 has to be equal to T1. Well, Newton's third law says, well, they have to be in opposite directions, but here you have pulleys and springs, and the directions are modified. The magnitudes of the two tension forces still must be equal to each other. Well, knowing this, so the first question that they're asking, find the acceleration of the two blocks. Well, the two blocks are tied together, so whatever is the acceleration of the first, the same acceleration in magnitude is of the second. So to find the acceleration of the first, well, the normal force and the weight cancel out. If they didn't cancel out, the block would fly above the surface or sink below the surface. It doesn't happen. So they cancel out. The only uncanceled force is the tension force T1. So you can say that force T1 is equal to the mass of the object M1 multiplied by, hold on, is equal to the mass of the object multiplied by its acceleration, right? Newton's second law, the net force is equal to mass times acceleration. I don't write vector signs because the directions are x direction right here. I don't need vector signs. Well, in this equation, there are two unknowns, the tension force and the acceleration. So I need to analyze the second block. For the second block, there are two forces. So the acceleration is going to be in positive direction downward. So the two forces are going to be the weight W2 in positive direction, and the tension force, which is the same tension force like the one acting on the first block. This is the net force. The net force must be equal to the mass of the object multiplied by its acceleration. And that acceleration is the same like for the first block. Well, now you have a system of two equations with two unknowns, and you just have to solve that system. How to solve it? Well, they're asking in part A, find the acceleration, so you have to exclude tension. So substitute the tension right here with its equal, and the equation is going to look like this. The weight of the second object minus m1 times the acceleration is equal to m2 times the acceleration. Now, this is equation with one unknown. Move this term to the other side of the equation with opposite sign. You have the weight of the second object is equal to m2 times acceleration minus or plus m1 times acceleration. Factor out acceleration, you get the weight is equal to acceleration times m1 plus m2. And therefore, the acceleration of the system is equal to the weight of the second object divided by m1 plus m2. So this should be the answer. And this answer is reasonable, both dimensionally and from a point of view of common sense. It tells you that the heavier the second block, the larger acceleration you're going to have, which is clearly reasonable. Okay, any remarks so far? If not, part B, find the tension. Well, you already found the acceleration. You can substitute it right here, and it gives you the tension in the cord. So the tension in the cord is going to be here. T1 is going to be equal to m1 times, instead of acceleration, you write the weight of the second divided by m1 plus m2. So this is the tension. Okay. So questions and remarks?
So since Weberstein wants like a numerical number instead of just the equation, I know W2 would be like M2.
W2 is given actually in this particular problem. It is the weight of the second object, which
Newtons.
for my version is 200 newtons. For your
Okay.
version is.
So what would like M1 and M2 be?
Oh, you have to find the masses. Oh, yes, I forgot to find the masses. Okay, so you have the weight of the first is m1 times g. Therefore, the mass of the first is g divided by the weight that they give you. The similar, exactly the same way, the mass of the second. So if the weight of the second is 200, 200 divided by 9.8 should be of the order of 20, a little bit more than
That was all.
20 kilograms. Okay, so I think that, well, if you don't have other questions, I have here examples, which I probably don't want to I have as examples, I have some examples from the from the textbook and other examples. But it would be better if I solve maybe some other homework problem. Do you have any other homework problem? People online? A homework problem from homework 4? Okay, let me solve problem number 19, apparent weight problem. Apparent weight problem. Problem number 19. So a person stands on a scale in an elevator. What is the apparent weight in each of the situations? Now remember, apparent weight is the magnitude of the normal force. So apparent weight is the force with which the floor acts on your body. And that force is the normal force. So this is apparent weight. So let's draw a diagram. So problem 19. So here is the floor of the elevator. Here is the person standing there. And they give you the mass of the person. What is the apparent weight? When the elevator is accelerating upward with given acceleration. So, first question, acceleration is this way. A acceleration this way, and it has certain value. Now, let's have a coordinate system. Which direction should we choose as a positive direction? Well, let's choose positive direction to be up. So coordinate system with positive y-axis up. So in this coordinate system, the acceleration vector is a positive number. So we're looking for the apparent weight. So the forces acting on this person are the weight, which is mg, and it is given because we know the mass, and a normal force in vertically upward position. So there are no other forces. Right? There is no friction because nobody is pushing in parallel direction. The net force acting on this person is F normal, positive, and the weight, the gravity force mg, negative. This is the net force. That net force has to be equal to what? To his mass times his acceleration. Well, his acceleration is given. Everything is given except the normal force. So we find the normal force and we say the normal force is his apparent weight. It's nothing different. So you say F normal is equal to MA plus MG. So you can say F normal is the mass times the acceleration plus 9.8. Now, in the coordinate system that we have chosen, the acceleration is a positive number. G is a positive number by definition, 9.8. So when he's accelerating in upward direction, he's going to feel his apparent weight. He's going to feel that he's heavier than normal. Because when he's at rest, his weight is mg. Now it is mg plus something, plus ma, plus some positive number. And that positive number you enter in part A. Part B, when the elevator is moving upward with constant speed. Well, when the elevator is moving with constant speed, the acceleration is zero. So all what we have written is here is correct. Just the acceleration is going to be zero. And the result is going to be that his apparent weight is just going to be mg. His normal weight is real weight. And part C, what is the apparent weight when the elevator is accelerating downward? Well, when the elevator is accelerating downward, the acceleration is going to be negative. In this case, negative 1.8. And here you're going to have negative 1.8 plus 9.8. And the result is going to be apparent weight that is smaller than his real weight, than his gravitational force. So you see that in order to solve those apparent weight problems, and they're going to be problems that are actually people make mistakes on tests, you need two things. You need to say that the apparent weight is the normal force in reality. And second, you have to have a diagram with consistent direction, positive direction, and you have to keep track of the algebraic signs. After that, you just apply Newton's second law. The net force, here it is, this is the net force, is equal to mass times acceleration. That's it. That acceleration could be positive, could be negative, could be zero. Okay. If no other questions, let me. Okay, problem number 18 in the homework assignment, it is about Newton's law of gravitation. So space traveler weighs 545 newtons on Earth. What will be his weight on another planet with radius 3 times that of Earth and mass twice that of Earth? Let's see. Okay, so his weight on Earth, W1, his weight on Earth is gravitational constant, the mass of the planet Earth, call it M1 or call it ME for Earth, times his own mass divided by the radius of the planet Earth, squared. So they give the value of this weight, right? It is, for my version, it is 545 newtons. So this is 545. If I want it, I can calculate his mass because gravitational constant is known, the mass of Earth is known, the radius of Earth is known. But I prefer not to. Instead, I write the equation for his weight on the other planet. So his weight on the other planet is going to be W2, and it is going to be gravitational constant times the mass of the other planet. And they say that, for my version, they say that the mass is twice the mass of Earth. His mass is, of course, still the same. And they say that the radius is three times the radius of Earth. Now, remember, you have to square the entire radius. And now look, this factor of 2 and this factor of 9, I can factor out. So I have 2 divided by 9, and you have gravitational constant, mass of Earth, the mass of the person, divided by the radius of Earth squared. This number is exactly his weight on Earth. Therefore, his weight on the other planet is going to be 2/9 of his weight on Earth. So even though the other planet is more massive, because the radius is larger, you're farther from the center, your weight is going to be lower, substantially lower, actually. 2/9 is substantially lower weight. Okay, now let's solve problem number 17. So this was problem 18. Did we solve 19?
Yeah. Yeah, you can mention.
Okay, so this was 18. Let's solve problem number 17. Again, a problem about Newton's law of gravitation. So problem 17, Newton's law of gravitation. Synchronous satellites are placed in a circular orbit that is certain distance above the surface. What is the magnitude of acceleration due to gravity at that place? Well, so look, the weight of an object is the gravitational constant times the mass of the planet Earth times the mass of the object divided by the radius of the planet Earth squared. When the object is not on the surface of the planet Earth, instead of the radius of the planet Earth, you have to replace it with the distance between the center of the planet and the satellite. So this, they say, it is 3.57 times 10 to the 7. So you have to replace the radius of the planet Earth with the radius of the planet Earth plus the number that they give you. 3.57. 3.57 times 10 to the 7. Times 10 to the 7. Right? Newton's law of gravitation, in denominator you have the square of the distance between the center of the first and the center of the second object. So when the object is very far from the surface, you have, to the surface you have the radius of the planet, and after that you have some height, which they give you. So this combination right here, this combination is the acceleration due to gravity. So this is what we call 9.8. Right? This is our 9.8. Now, when we substitute the radius of the planet Earth squared with this number, you're going to get, instead of 9.8, you're going to get some different expression. So, in other words, your new acceleration, G prime, is going to be gravitational constant, the mass of the planet Earth, divided by the radius of the planet Earth, plus the number that they give you, 3.57 times 10 to the 7th, everything squared. Everything in the denominator is squared. And this is going to give you the number that they want. That acceleration is clearly going to be smaller than 9.8 because in denominator you have a larger number. Make sure that when you substitute the radius of the planet Earth, make sure that it is in meters. So that, not in kilometers like they usually give it. Okay. I can do one more problem, but let me give you opportunity to okay, let's do the following conceptual questions. Okay, so this is, I'm going to read the conceptual question and people online may answer. So, you put a book on the bus seat next to you. When the bus stops suddenly, the book slides forward off the seat. The question is why?
You can't see right there.
Uh,
There you go. You were just in the.
oh, I was, oh, so,
Yeah, you're
okay,
good,
so,
you're good.
but they can never read the, they can never read the screen, can they? I
No.
doubt it. They can never read the screen, it is true. So the option is, a net force acted on it, no net force acted on it, it remained at rest, it didn't move but only seemed to, the gravity briefly stopped. What would you choose? What do you say? This is a tricky one. Well, there was gravity, but that gravity is exactly cancelled by normal force. Why did it move? Well, in reality, no net force was acting on it. Well, assuming no friction. What happened was that it was moving with the speed of the bus. And it kept moving with the same speed along a straight line. That's it. No net force was acting. Didn't accelerate. The bus did. The bus stopped or decelerated or whatever. But it was just moving along a straight line and there was no net force acting on it. Right? That's a tricky one. So follow-up question. What is the force that usually keeps the book on the seat? Well, usually there is sufficient friction, so even if the bus stops suddenly or accelerates fast, the friction holds it. You see? Okay, let's go to the next one. You kick a smooth flat stone on a frozen pond. The stone slides, but eventually slows down and stops. You conclude that. What is the best conclusion? What would you say? Let me see show of hands, maybe in the chat room, if you see the screen. what would you say? There are no penalties here, so, okay, you say three, you say no, unenforced acting on it all along, okay, what about, what would be your guess? Okay, so we have consensus. And indeed, well, it slides, but slowing down. This means there is some acceleration, therefore there is some net force acting on it. What is the net force? Well, gravity is canceled out by normal force. The only force that is not canceled out is the kinetic friction. Okay? Very good. So notice how tricky the other options were. Right? You may become tempted to say, well, the stone simply ran out of steam, right? That's perfectly down to earth and calm. Or the stone has natural tendency to be addressed. So keep in mind that tricks like that are often encountered in any tests. Okay, so let's wrap it up. Uh, okay, so don't forget the midterm. If you have questions about the midterm, well, I'm open for discussions.
Should I end it?
Yes, first end YouTube because it continues recording.
Stop live stream.